So as we move forward into the correlation testing for a linear correlation, we're going to now look at actually creating a hypothesis test. For this lesson, when we create a hypothesis test for this population correlation, again, we're using this Greek letter rho as our population correlation coefficient. Again, when we create a hypothesis test, know how we have to have the null hypothesis and the alternative hypothesis. For us, when we do this here, we're going to be doing what's called a two-tailed test. So basically, it's a yes or no kind of concept. Is the population correlation coefficient significant or not? Yes or no. So again, our equality is going to be the null hypothesis, which means in this case, no significant correlation. And then the alternative hypothesis rho is going to be not equal to 0. That means there's going to be a significant correlation. And since we're using not equal to 0, that tells us that we're actually going to be using a two-tailed test. So as we move forward, we talked about how to find a critical value using table 11, but we also want to create what's called the test statistic. So to find the test statistic, we actually have to use what's called a t-test. So to find a t-test, what we have going on here is this is going to be the strategy to actually determine the actual test statistic. But notice how this formula is a little bit involved. Notice that when we do t-tests, there's this degrees of freedom. But notice that since we have a two-variable stat question, notice that when we do the degrees of freedom, actually we don't use n-1, we use n-2 when we are working with t. We lose one for each variable, if you will. So that's something to kind of pick up on here. Now, instead of using this formula, we can use a calculator to find this test statistics. So if we go to stat, go to test, I think it's like F or something. It's way down here. Yeah, this one that says linear regression t-test. So that's kind of the one I want, is that one. So let's see if I can get this to work here. So we're actually going to use stat. We're going to test. The one we want is this linear regression t-test. So linear regression t-test. T and test, two T's. So that's the button we want to use, and it's actually going to create a lot of our math for us here. So that's what we're going to kind of pull away from here, is this guy right here. Okay. So these are some things we want to pick up on. Is to do a hypothesis test, we're going to use rho as our population correlation coefficient. And we're going to be using a two-tailed test. So rho is going to be not equal to 0 in that situation. So let's move on down and we go through our checklist. So to do a hypothesis test for the population correlation coefficient rho, the first thing is the question, it has to say somewhere about, let's see here. We want to identify the null and alternative hypothesis. So H sub 0 and H sub A. We need to specify the level of significance, which is going to be alpha. We're going to identify the degrees of freedom, which is going to be n-2. We're going to determine the critical values from a table. So we can use the t distribution table, or we can also use inverse t. So inverse t, remember that's in the distribution area on the calculator as well. So if we go to distribution, that's going to be the inverse t. Now, And then to find the actual test statistic, that's when we're going to be using the linear regression T test, I believe is what we said. That's going to be that one to get that's going to save us some math there. So we have a few things that we have to kind of find on our calculator or tables. Again, the t-distribution table is not that bad, so you're more than welcome to do that, but I'm thinking I'm just going to just let the calculator do most of my work here on this problem. So let's see what we got going on here. So again, if t is in the rejection region, then we reject h0. Otherwise, we fail to reject h0. And then we interpret decision from there. Okay. So let's move into our problem, see if we can put this all together. So the number of hours 10 students spent studying for a test and their scores on the test are shown in the table. Is there enough evidence to conclude that there is a significant linear correlation between the data? Use alpha equals 1%, if you will. So I'm going to pause the video and put the data in the calculator to start with. So I've got my data in the calculator. So I could, if I want, look at the scatter plot just for the heck of it. So if I hit zoom number 9, and if you look at it, it looks very linear just by looking at it. So right now, as long as I stay within this sample, it looks like it's a good predictor. But let's see how it plays out with the actual population. So I'll go ahead and put that and play this out here. So as we do a hypothesis test here, since we're doing a population correlation, we use h0 is going to be rho equals 0. And again, if you want to make this a little bit fatter looking, and then alternative hypothesis is going to be rho does not equal 0. That's going to be your alternative. So basically, again, this is not significant. And this is going to be significant. So if we don't reject H0, then we're saying there is basically no correlation. It's not significant. But if we're rejecting H0, then we are saying there is a significant linear correlation with the sample and the population. So the level of significance is alpha, which is going to equal 0.01. Now, since we're creating critical values in a rejection region, again, we're talking about the t values. So again, since this is a two-tailed test, we have to find negative t sub 0, and we have to find t sub 0. So I usually kind of like to draw this out to create my rejection region. So my rejection region is going to be left of t sub 0 and right of t sub 0. And remember, 0 itself is here in the middle. So to find these critical values, if alpha is 0.01, since it's two-tailed, we actually got to go 0.01 divided by 2. So if I do that on the calculator, I think that's what, 0.05 or 0.005. So we have this 0.005. So 0.005 is going to be the area under the curve here. So what I want to do is find this area over here to the left, and I'm going to be using inverse t to do that. So I'll be going to the distribution area using inverse t instead of the table, t distribution table that is. Notice that the area is going to be this 0.005. Now the degrees of freedom, we have to actually use n minus 2 for the degrees of freedom, since this is a two variable problem. So since there's 10 students, we actually have 10 minus 2, which is 8. So 10 minus 2, which is 8. So 8 degrees of freedom. And if we put that into the calculator, And I can never remember where this wants to round it to. Let's go 3 decimal places. So notice that, the critical values then are going to be, so negative t sub 0 is going to be like negative 3.355. But because of symmetry, we also know t sub 0 without doing any calculations, t sub 0 is just going to be just dropping the negative 3.355. So these are my critical values here, negative 3.355 and 3.355, 3.355. So if I am left of negative 3.355, or if I'm right of 3.355, I'm in the rejection region. So to find this test statistic, this is where we're actually going to use the calculator instead of this formula up here. So if we go to stat and go to test, and if we go down here to this F, this linear regression t-test, notice that my list was in L1 and L2. That looks good. And notice that row does not equal to 0. That's good. So all that stuff looks good. Hit calculate. And all I really need from there is my t-value. So my t-value here, my test statistic, is going to be this 9.341 if I go out 3 decimal places. So notice that based on that, 9.341 is going to be out here. So that is going to be in my rejection region. So I am going to reject H0. So for rejecting this, we are saying there is a significant linear correlation here. So it looks like studying for a test and making a good grade on a test. So as the hours increase, your test scores increase. So that's even like a strong positive linear correlation. I don't know if this gives you your R value here either. It looks like this only gives you your other stuff here. If I want that R value, I'd actually have to go somewhere else for that. Don't think there's anything else here or not. Yeah, it does actually give you your R value here too. So it's interesting. So it does give you R value here as well. So notice that your R value would be this 0.957. And notice how that is really close to 1 as well. So it does give you a lot of information here. Didn't realize there's a little down arrow there that says keep on going down. And yeah, there's that R value as well. So that linear regression t-test does give us a lot of information there as well. So that kind of is where you would go if they actually asked you to do a hypothesis test there. Hopefully you find that useful.